Good morning, everybody. Well, thank you, Corey. So, um, thank you, Matthew. Well, I was talking about residue theorem and one of its applications, uh, which is finding value of an integral, especially improper integral that I'm going to talk about today. Uh, when we know the integral converges, uh, but after converting it to complex integration, we can find its value by using the residue theorem. Okay, well, let me go to my whiteboard. So the first thing I talked about was uh, those integrals that are from 0 to 2 pi, and it's combination of sine and cosine, all right? Um, uh, in general, I will say f of k cosine theta and sine theta, then you integrate with respect to theta. So for this type of integration, we learned, and I gave you an example, that how we convert this to integration over a unit circle, all right, by simply choosing z to be um, e to the I theta, all right? And by that change of variable, sure, dz or d theta is going to be uh, dz over iz, okay? And cosine theta, which is e to the I theta plus e to the negative I theta. So it will be z plus z to the negative 1 over 2, and sine of theta will be, yeah, just using definition of sine, it here is 2i z minus 1 over z, okay? By this change of variable, we converted this integral into a complex integration over unit circle, and then uh, use the residue theorem to find the value of the integral. Now, then I talked about the improper integrals that, especially when the function is even, the improper integrals from negative infinity to infinity, f of x dx, all right? And when the function is even, this is going to be twice integral from 0 to infinity, f of x dx, all right, when f is even. Okay, then what happened, you're supposed to, for example, find a value for this, but when the function is even, you will work with this one, and half of that will be this one. Now, we will convert this to a complex integration, all right, over this contour. So in this case, the contour that we consider would be the semicircle. All right, the semicircle. Here is negative r. Here is r. And I said, okay, let's call this semicircle just CR. This is x-axis. Here's y-axis. So this is the CR, okay? So we consider f of z and we integrate over this closed contour, this closed curve. And by residue theorem, it says that, okay, whenever you do this, the answer will be 2 pi I, the residues at the poles at singularities of which are inside this. And later we let R approach infinity. So here is what happens. Uh, instead of f of x, we go with f of z and say, look, negative r going uh, counterclockwise, okay, going negative r to r. F of z dz in this case will be f of x dx plus the integral over the semicircle, the integral over CR, f of z dz. That will be 2 pi I some of the residues that are inside here, right? And since we are going to let R approach infinity, it will be residues on the upper half plane. So the sum of residues of F as, let's say, Zi. We don't know how many. So this is Zi's are the poles of the function on the upper half plane. So Zi is the pole of f of z in the upper half uh, plane. Good. So in this fashion, um, this equation is perfectly fine, but we let R approach infinity. When R approaches infinity, this will give us negative infinity to infinity f of x dx. That is what we are after, okay? How about this one? Well, this one uh, definitely when you're dealing with a fraction and degree of top is 2 less than degree of denominator will go to 0. So, and we use this fact. If degree of P of z, this numerator, is less than or equal on degree of denominator, maybe I should add, if we add a 2 here, plus 2 degree of denominator. So this means degree of denominator is going to be at least 2 higher than. If this happens, then the limit of this ER PZ over QZ this limit as R approaches infinity will be 0. And it's easy to prove this by using ML inequality, okay? So this will take care of 2 types of integrals. Now, to explain this, especially this second part, although last time I gave you an example, let's have another example today, because this is such an important part of complex analysis. In fact, for elementary complex analysis, this is what we are doing. It's elementary stuff. This is the best part of complex analysis. All right. Look, here I'm going to, as example, find the value of this integral, 0 to infinity. Let's make it a nice one, dx. Here is 1 plus x squared. How about that? We know that from calculus 2, this integral converges, all right? But in calculus 2, we were not able to find its values. We could only say, oh, this integral converges, gives us a number, okay? Now, to calculate its value, first of all, you realize that the function that we are integrating is an even function, okay? So let me make sure that we do this. Note that this 0 to infinity of this function is 1/2 negative infinity to infinity, because the function is even. And now is the time to convert this integral in complex. So in complex, as you I said earlier, for this type of functions, we are going to consider this semicircular region or contour. Okay, not a perfect semicircle, but just yeah, y-axis, x-axis. We call this one CR. Here, negative R to R. Okay, so um, the function we are considering is this one. Consider f of z. Well, nothing special, just this function replace x by z. 1, 1 plus z squared, squared. Consider this one and this contour. And we will make R big enough to make sure that all the poles of this function would be inside this, all right, normal forms. But the poles are zeros of denominator, right? So z squared equals 0 will give you z equal plus minus I. But minus I is outside. We don't care about minus I. I is here. Okay, good. So um, the integration over this contour will be just 2 pi I residue of this function at this I. So the equation that I gave you earlier is this. Going from negative R to R counterclockwise over that closed curve. So negative R to R, f of x dx, plus going on that semicircle, called it CR, f of z dz. It's going to be 2 pi I residue at this I. Done. Okay. Residue of the function at that point I. Oh, we can easily compute this, right? Oh, in order to compute, of course, you need to realize that this I is a pole of order 2, okay? It's pole of order 2. So the uh, residue in this case is going to be, yeah, just let's calculate residue. Um, so residue of f of z at this point I is pole of order 2. So you multiply by z minus 2 squared, and then you take derivative. Okay, you take derivative. So by the way, if we go ahead and do that, we are going to get a 2 or 8 5. Okay. So um, so we know what the value of this right-hand side is after multiplying by 2 pi I. Uh, okay. we'll get just pi over 2. But although you don't need to do this in your tasks, your homeworks, but I am doing it just to make sure that you understand why the limit of this guy as r approaches infinity is 0. And then we will let r approach to to show that this goes to 0, we will use ML inequality, all right? ML inequality. So here is CR, f of z, and you know what f of z is, it, right? dz. Modulus of this using ML inequality is less than or equal to length of curve. Here, the radius is r, so it's half of it is pi r. The upper bound for f of z, here is f of z. When z is on CR, modulus of z is r, okay, the radius. So this will be less than or equal to 1 over r squared minus 1 squared. Oh, look. Of course, as r approaches infinity, the degree of denominator is r to the 4th, here r. So this goes to 0 as r approaches infinity. Okay, just make sure that you understand why that part goes to 0 using ML inequality. And as a result, you, from this equation that I write here, I have here, you let r approach infinity here, you get negative infinity to infinity, all right? So negative infinity to infinity of f of x dx. That's what we wanted. This goes to 0. Here, the residue we calculated 2 over 8i and multiply by 2 pi I, you will get pi over 2. But sure, we wanted 0 to infinity, right? So therefore, 0 to infinity of f of x dx, the value of this integral is pi over 4, half of that. Yeah, an example. It's a beautiful application of this residue theorem. Okay, beautiful application. So, an extra example for you to make sure that you got the, you know what's happening. We just got 2 examples. One, functions of this format, we converted to unit circle, and then functions of this format, we converted to, again, a complex integration. Now, what if we have combination of uh, combination of trig functions and uh, let's say uh, algebraic function. What if you have something like this? Let's say 0 to infinity or negative 0 to infinity. We both have f of x and some sort of sine and cosine involved. Let's say cosine of, for example, kx dx, or it could be sine 0 to infinity f of x sine of x or 2x or 3kx or in general kx. K is the number, dx. So how do we take care of these type of uh, integrals? And of course, if the function is even, this will be half of negative infinity to infinity. And even if it is not from negative infinity to infinity, they call it principal value of, or Cauchy's principal value of the that integral. Oh, Brandon, are you talking about the let's see, Brandon has a question. Are you talking about this part or ML inequality? Okay, good. Well, um, here is why such a thing happens. Remember, so modulus of z is r. And we are talking about when z is on this curve. So modulus of z is always r. Then what happens to this function right there? What is the upper bound for this function? Well, this 1 plus z squared modulus is bigger than or equal to modulus of z squared minus 1, right? That's triangle inequality number 2. So it will be here z squared minus 1. And this is r. That is when r squared comes in because modulus of z is up. Now, so let's put it down. But you have 1 plus z squared, right? Square of this guy. So 1 plus z squared squared will be bigger than or equal to, this is r minus 1 squared. Now you took reciprocal. When you take reciprocal, it will be modulus of the function. This is the function. Modulus of function. So this is, when you take reciprocal, the direction changes. That is how we use ML inequality. This is your M, all right? This is your M. That is your M. So f of z, this is f of z, this is M. less than equal to this. L is the length of the curve is this. So it's pi r over this. Of course, as r approaches infinity, you get 0. All right, good. So that's it. Now, going back to, okay, going back to this. How do we treat these? Well, in this case, the function that we will consider will be f of z. Oh, we don't consider cosine something z or sine z. No. Instead of that, we will consider e to the, all right, e to the something. So e to the I k z. So in this case, we consider f of z e to the I k z. And we integrate this over the same semi-contour semicircle closed curve that you already know. All right. So we consider this one and integrate over this guy. Same thing, negative r to r, and here's CR. Counterclockwise. Okay. So the formula that we have for this particular one is this, that the integral from negative r to r this guy, f of z, oh, in this case, because on the x-axis, right, z becomes x, f of x, e to the I kx dx plus the integral over CR, that function, it's going to be 2 pi I residues, all right? 2 pi I residues are in here, some of the residues. As before, okay? I'm just putting 2 pi I, some of the residues, but we know that residue of the poles that are in here, and we make R big enough to include all the residues in the upper half plane, okay? All the residues in the upper half plane. Good. Oh, well, interesting enough, this part is going to give us, because e to the I kx is cosine kx plus I sine kx. So if we split this into those using Euler's identity, we will get both of them. And we need to have this as r approaches infinity to go 0. All right. And this happens when definitely when f is a fraction, degree of numerator is 2 less than degree of the denominator. All right. But because of this guy, uh, we don't really need degree to be 2 bigger. 1 bigger will be enough. And that's um, right. So in the process, Del Dodson, you are going to get your answer because um, you want to make theta here or theta or x. Those are dummy variables, all right? Doesn't matter uh, which letter we use. Those are dummy variables. But the last uh, comment that I made was this. We use e to the I kx, or you want to I k theta, all right, theta. That's a dummy value as cosine of kx plus I sine of kx. So if you use this one here, we will have two integrals. Right? One of them has cosine of kx, the other one sine of kx, but with I. We need to make sure that this goes to zero. All right? So here is a fact. Here is a fact. In this case, I don't need the degree be two more. One more would be enough. If degree of denominator is bigger than degree of numerator plus one. If it is plus two, perfect. But we don't need uh, uh, plus two, plus one is enough. If this is true, then this integral, the limit is going to be zero. Limit of CR, again, using ML inequality, and that there is another inequality called Jordan's inequality. Jordan's inequality also will be used here. So Q is the PZ over QZ. Then e to the IKZ dz. This limit is zero by using ML inequality, all right? So uh, the proof so uses Jordan inequality, and so the proof of this fact in the proof, why maybe I say in the proof we use not only ML inequality, but and there is another inequality called Jordan's inequality. I might talk about Jordan's inequality today. Okay, good. So here is the key. Here is the key. I am going to give you an example and work that example to make sure that you see the process. We want to use one of these. In fact, with this, we will get both of them. So you will consider f of z e to the I k z, okay? And you integrate over this contour. Integrating over this contour, this part will give us both of those. This will go to 0. And on the right-hand side, you have 2 pi I residues of this function on the poles that are in the upper half plane. Okay, that is the our strategy. And here is an example. Here is an example. Let's find the value of this integral. Find the value of 0 to infinity. The function that I'm using would be x sine x divided by x to the 4 plus 16 dx. How about that? See, this is what I called f of x, and this is sine of kx. Oh, that k here is 1. It could be 2, it could be 3. In general, it can be k, but in the process, it doesn't really matter. So, what is the process? We will consider this function. So, consider I'm going to call all of it f of z. Oops. This is these, all right. But for sine x, we don't use sine x. We use e to the ix, iz. So z e to the iz divided by z to the 4 plus 16. And we integrate this over that semicircular contour, right? So what do we get? Oh, by the way, this is an even function, all right? And so maybe I should emphasize that. Note that f of x, well, just this one, x over sine x, just this one, the integrand, is even. Okay. Being even, therefore, the this guy, we want to find the value divided by just is 1/2 negative infinity to infinity. Okay? Because if we want to integrate this guy on that semi uh, circular contour, we get this one. So good. Good observation. So integrating f of z over that contour will give us negative r to r f of x dx, right? Because it's on the x-axis. And by f of x, I mean this, f of x dx plus that semicircular f of z dz will be 2 pi I residues, okay? Sum of the residues, and I'm already know that this denominator, all the residue, all the poles, all these are simple poles. There are 4 of them. 2 will be in the upper half plane. So I'm going to call Z1 and Z2 residue at Z1 plus residue at Z2. Why do I say this? Because the poles are zeros of denominator, and zeros of denominator, Z to the 4 plus 1 equals 0 means, which is e to the pi I plus 2 pi I, 2k pi I, right? So then z will be e to the pi plus 2k pi all of it I divided by 4. So k can be 0, 1, 2, 3. All right. For k equal 0, 0, you get z1 and for k equal 1, you get z2, which is 3 pi. Oh, these are in the upper half plane. The other 2 will be in the lower half plane. I don't need those, okay? So z uh, residue at this one and residue at this one. And these are simple poles, all right? These are simple poles. when it is simple poles, we can use, for example, I already called it 2b. So residue at, let's say, is Z1. It's numerator divided by derivative of denominator. All right, here is numerator. Derivative of denominator is 4z cubed. Well, one of the z's cancels. Then you replace z by z1. Okay. So did I right? That's good. We know how to compute this one, all right? I'm not going to go through all the computation. Same thing. Residue at Z2 will be numerator divided by derivative of denominator. When you replace by Z2. Well, here we get a number, here we get a number, right? And limit of this guy, the middle guy here, is going to go to 0. Derivative, oh, look at this. Degree of numerator is way, way smaller than degree of denominator. So also limit of CR as R approaches infinity of f of z dz is 0. So that will give us through this guy as R approaches infinity. This will go 0. Then we will have negative infinity to infinity, okay? And on the right-hand side, we know how to compute this one. So I will let you finish and go through all details. So here is then negative infinity to infinity of f of x dx will be 2 pi I residue at z1 plus residue at z2. Done. Now, here is, well, when Del Dodson's question comes and becomes very important indeed, f of x, which is this one, by the way, here is f of z. So f of x, here you get e to the ix. And if I replace e to the ix using that Euler's formula, I'll have x cosine x plus I x sine x. So in the uh, left-hand side, actually we have two integrals, negative infinity to infinity, x cosine x, 1 plus x to the 4. Oh, was it? Oh, 16 plus x to the 4, sorry. All of it 16 because I have 16 here. So, oh my goodness. Nobody noticed, huh? Okay, good. So here, this one becomes x to the 4 plus 16 dx plus I. Negative infinity to infinity. Now x sine x. So we get both of them, not just one, both of them on the left-hand side. Is whatever we have on the right, okay? And the real part will be equal to this. The imaginary part of that will be this one, okay? So in this process, actually, we found uh, the value of two integrals instead of one. Any comment, any question? Don't see any question. Yeah, but you're right. We wanted just the one attached with sine x, but we got the other one for free. Right? So uh, we got the other one as well. And that is the nature of this problem, this process. Although you want one attached to sine x or could be cosine x, but at the end, you will get both of them. Okay? Any other comment, question? Well, after we compute this one, the right-hand side, this is going to be a complex number. Its real part, it will be like a plus bi, right? This is going to be a plus bi. And then a will be this, because it's real. You have this equation, two complex numbers being equal, right? So the real part will be this part. Then the value, which is, as you said, attached to sine x, will be b. So that is how, with in this process, we get the value for both of them. All right. Any other question? So still, I am in. I was in uh, 16.4. This 16.4 is so important, so fascinating that that is why I spend a lot of time on it. So um, you can now do in 16.4 some of the problems 16 through 20, uh, yeah, 21, where you have some sine and cosine also involved, all right? 16 through 22. 16 through 22. So here, please be very, very uh, um, careful about this section. This is a extremely important section, and in your next test, you're going to have uh, definitely questions from 16.4. So this is 16.4. Oh, uh, that section is fascinating section. In this, very briefly explain things in here. But I can still talk about that section for uh, 2 or 3 more sessions. But I don't want to fall behind. Um, uh, right, the value of B. That's in this case, since we were talking about uh, x sine x divided by x to the 4 plus 16, yes, that would be just B. Uh, we need that B. Okay, so please work on these problems. Okay, uh, as I said, I still can talk about this section. There are many other types of integration to work on, but I will stop at this point, and next time I will start chapter 17. Right, another chapter. Any comment, any question? If there is no question, then have a good day, everybody. I will see you on Thursday. Bye-bye now. Thank you, Krish, Rochelle, Corey, Matthew, Del. Thank you, everybody.